I start? Or? Okay. All right. Last time, we hopefully agreed essentially that whenever we have something topologically invariant, so homotopy invariant, and the homotopy being defined for continuous function, we kind of can easily extend it to Sobolev maps, right? That's kind of an abstract nonsense theorem. Any kind of quantity that measures something homotopy invariant can be defined on Sobolev spaces in this critical scaling. And okay, that's just good. However, sometimes we need more information, more precise information, and then we cannot use just abstract nonsense results like the one we just proved, but we need then more precise structure about what we're talking about, like the degree. And the example that I mentioned at the end the last time was this, this theorem, which says, assume that F goes from the n-1 sphere to the n-1 sphere, degree not zero, smooth, whatever, and then there exists no F in W1n on the ball into the sphere, or into Rn, such that the rank df is less or equal than n-1 almost everywhere, and F extends little f, right? So that's a type of result where we kind of need the structure of what the degree is more than just an abstract understanding of the degree. If we want just here something like F maps into the sphere instead of this sort of assumption, okay, we can work abstractly. But for this, we need to work a bit harder. And this is, as you will see, I will try to tell you a few examples today. In questions like those, we really need to look at the degree, understand the degree, get a nice analytic formula for the degree, then we can do something. And if we have like a different setup with different spheres or different assumptions, then we have to do, again, do some algebraic topology, like some simple one, get a different formula, deal with that formula, and we get something. We don't have this everything works for everything kind of situation anymore. All right, so the main point for this theorem, as I have mentioned at the end the last time, is that the degree of F can be written as pullback of a differential form. There is a, well, homological or cohomological formulation of the degree if you want, right? I mean, there's something about differential forms, very analytically traceable. That's very important. Now, I would like to discuss this because we have to talk about differential forms a lot. So I want to have like a short, I don't know, 50 minutes or something, just going through differential forms and that we are all on the same page. You may also have seen, which is exactly the same, right? The winding number itself, I may screw up constants, but other than this, this is correct, is this formula. Right, so you have a map from the one sphere to the one sphere, then the degree can be computed by the first component of F, tangential derivative, right? I wanted to stress this. Then F2 minus F2 dF1, right? And more generally, you may have seen this formula on Sn-1, which is horrible, but it's exactly that formula. Again, you know, signs and stuff may be wrong. So you take the determinant, df is an Rn-1 vector, but f itself is an n vector, right? So we cannot take the determinant of the whole gradient. But we need to make a selection. And I had this with I minus 1, dfi plus 1, dfn. that determinant, then alternating in I, this in on the sphere, that's the formula for the degree as well, right? So you may have seen this formula, or that formula, and of course they're all the same. Okay, and I hope you see the advantage of using that formula. There's nothing then more than algebraic preferring this formula over those. This is very long, this is very short. Okay, but those are all the same formulas. So, in order to hopefully are all on the same page, let's quickly talk about differential forms, right? I use them not really in some homological, cohomological sense. It's just like, you know, shortened formulas, right? So, K form, let's be on Rn, is simply an element of the vector space spanned by the basis, and the basis is just these wedge products of differentials. So a K form omega is simply saying omega can be written as I1 strictly some ordered sum, K of them less than N, and then we have dpi1 wedge dpi2 wedge dpi K, and there's an omega I1, I2, Ik. Okay, that's a K form. We don't care really what this means. We just say they are all orthogonal to each other, and that's the K form, right? I don't care about this definition about duality or anything like this. All right, good, right? So this here is the basis elements. They're all different with different entries. They're all ordered, which is a nuisance now and then when we do operations. So yes, I1 is always less than I2, but we are just going to agree that if this is not the case, we just switch the sign. Okay? So then they can be ordered or unordered. We can always go back to that form. All right, good. So now we have a K form. Now we can talk about regularity of a K form, right? This omega, this entry, the vectorial coefficient, can change according to the point where we are at, right? And if it does so, we can measure whether it's smooth or not. So we say that omega, so K form we may write as this lambda K Rn, right? And then we say omega is a smooth K form, or a C1 K form, or Sobolev K form, if, by definition, we are on Rn, so I really don't have to do much work. If these guys vary, if P maps into omega I1, I2, P, that's a scalar function. We just want this to be in C infinity or in Sobolev or in C1, right? So now we have smooth forms, and I'm going to denote them like this. It's not always done right this way, but this is my lazy writing. Okay, so now we have something like smooth K forms on Euclidean space. Everything is on Euclidean space. This volume form, if you know what it is, right? You can just extend it somehow. Your favorite way to extend it. All right. If we want, say, to have the C1 norm be C1, we can also define this as a norm, right? This is a normed space. We just take the coefficients and norm, right? There's nothing complicated there. All right. Good. So now we have forms. We know what differentiability means, so we can take the derivative. We don't take the derivative, we take the differential. Okay? So, given omega like this, maybe I write omega of P, right? Then we can compute the differential of omega, and this is simply, I'm going to be lazy and just write I, and write dxi, right? And now I have here my omega I, and the differential is just differentiating this guy. So this will be d dxj wedge and whatever we had before. That's the definition of the differential, okay? You see, if omega is a K form, this here will be a K plus 1 form. Okay, so the differential takes K forms, K plus 1 forms. And this is the formula. Formula doesn't matter too much for us, but it has some consequences. If omega is scalar, so a 0 form, so then d omega is simply somehow the gradient di omega dxi, the sum over I. You just say, okay, this is somehow like the gradient, but okay, right? I hope you all know, right? Taking d cross d, so the second derivative is not the Hessian, right? That's the curl. So d of the one form is the curl of the entries, and then it gets more complicated. So it's important to remember d cross d is 0. It's just a computation for any form, right? And so it's not the derivative. The differential doesn't measure, unless you are a scalar, it doesn't actually measure the derivative, but something smaller, right? Like the curl. All right. In particular, just because the derivative is 0 doesn't mean that the form is constant or something like this, right? This is the Poincaré situation. All right. Good. So I want us to agree that this is a differential operation. This is important. The second thing that we need is the pullback. All right, so this here will be an n-1 form. I will say which one. Now we have this star is simply the pullback of a map F. Right, it's a bit bad because they have the same name, the domain and the target, but it takes the target guy and pulls it back into the domain. So we have to define this. So assume phi goes from Rn to R capital N, and we have a form here, a K form. Then phi can pull this K form back to here. That's essentially the chain rule. Right? So omega in, let it be C infinity K form on Rn, then phi star of omega, if phi is smooth, will be in C infinity, still a K form, but on R little n. Okay, and the formula is the chain rule. We just plug in the phi here, but we also have to replace these coordinates with phi. Right? So just so that we have seen it once, I write I, because I'm lazy. Then I write omega I. This is just the chain. And then we have d phi, first component, p wedge d phi I2 of p wedge d phi ik of p. All right, and this here follows according to this rule, to the differential. This here is simply, erase this, this looks weird. So d phi I1 is simply d over dxi of phi, call it j I1 dx j. And I sum from 1 to n. Okay, so that's the pullback. Slightly nicer written in my notes. If you want to actually read what I wrote. Important thing about, and this is really crucial, right? And this is true for the differential, but not for the co-differential, is d of phi star of omega is phi star of d omega. Okay, they commute. Without that, we wouldn't use this differential forms, right? This is extremely important. Okay. Now, one important thing, right? Here I talk about the rank. We will later see, or we saw in Yannick's talk, the diff curls, right? They all come out sort of Jacobian structures. That's how these diff curls were essentially discovered. In 2D, it's a Jacobian of something, right? The determinant of a gradient. And the whole point that you can do stuff right, like the diff-curl lemma, the Kaufmann-Liouville-Meyer-Sems or something like this, is that you have a Jacobian structure. With pullbacks, you always have a Jacobian structure. Why? Because if you just look at this guy, this is a subdeterminant of the gradient of phi and then a determinant. Right? There's a bit of computation, right? You have a lot of entries here, right? So you have a sum here, you have a sum here. They are all wedged. Some things cancel. But in the end, what this will be is, this will be the sum. There will be a sign, which I really don't care about. And then it will be the determinant of, take d, okay, so d of phi I1. This is going to be, right, I write d phi. And then we look at the, say, columns I1 through Ik, and we go with alpha 1 through alpha k, and we have dx alpha 1 wedge dx alpha k. That's the explicit computation. The sign you can compute yourself, not relevant for us. But whatever this is, it has so much symmetries that you can, I mean, you can also abstractly so that must be a determinant, right? And it only depends on these entries. So it will have this form where we sum over the alphas. Okay? So everything that we are going to do will kind of work because these here are determinants of gradients, right? And that's the same effect that we have in the harmonic maps regularity theory. Determinants, diff curls, they are diff curls, always have some compensation effects that we can try to use. Okay? For example, if these guys are in LK, this thing is in the Hardy space. Okay? All right, good. So, so we have this. And now, essentially, we just make an agreement. And the agreement is how to integrate on differential forms. And, well, in differential forms, on Rn, we simply agree that a scalar is integrated. This essentially fixes an orientation in this form. So if I have dx1 through dxn, and I have some f of x, what I mean with this is f of x in the sense of the Hausdorff or the Weg measure on Rn. Okay? That's how we integrate forms. So we can integrate n forms on an n-dimensional space. Right? Everything else doesn't make sense. Right? A k form on an n-dimensional space, we don't integrate. All right? Good. Yeah, maybe. So we are going to integrate on the sphere. How do we integrate on the sphere? Well, the nice thing about the pullback is that it tells us how to integrate forms. And so the formula, if phi is a diffeomorphism, is if we want to integrate on phi of m, a form omega, this is the same. That's a change of Reibel's rules. That's the nice thing about this Jacobians here. It's the same as the pullback of phi of omega on m. Right? So here I assume m is a k form, a k manifold, and this is a k form. Then this is the change of Reibel's formula. Again, you see it's shorter, and that's the advantage than the classical one, where we have to write a determinant of something. Okay? So this encodes the whole change of Reibel's. In particular, if you want to integrate on the sphere, let's think this guy is the sphere, or a part of the sphere, right? By a diffeomorphism, you just integrate on Euclidean space this guy, the pullback. Right? So if phi parameterizes the sphere, you know how to integrate now on the sphere. Okay? All right. Now, almost there, almost there. Important thing. So this is change of Reibel's. Integration by parts is also nicer with differential forms. If you want to integrate on a manifold, I put d omega here, then this is the same as omega on the boundary of the manifold. Right? And this is called the Stokes theorem. Again, if you just write things out in classical way, you see this is the integration by parts formula. Okay? Yeah, in particular, right? If we have a manifold without boundary, we integrate an exact form, it's 0, right? This will be nothing because this is the integral over the boundary of omega. There's no boundary, that's 0. Okay? All right. Okay. And now it won't be super used a lot, but I may use it, right? So you see, sometimes it's important, I mentioned this before, right? The differential forms, the differential is not the full gradient. So the gradient equals 0 is the actual information that's not just saying the thing is constant or something. So we distinguish between two types of forms where the differential vanishes. Closed forms is simply a form where the differential vanishes. An exact form is a form where omega can be written as a differential of something else. And the difference between the two measures a lot of topology. That's the cohomology group, right? That's the de Rham cohomology. If omega is exact, so omega can be written as d eta, then it's closed because d cross d is 0. But the other direction is not always true. It depends on the holes in your space, right? That's essentially the Poincaré lemma or the Hodge decomposition if you want, right? This factors in there. All right. This is, I think, all I wanted to repeat. Any questions? I think we all agree. All right. So, blah, blah, blah. I promised to talk about the volume form. What's the volume form? On the sphere, it's exactly that thing, but just written as a pullback, right? So we just encode it. So, volume form on the sphere. The volume forms are not unique. Well, how do we define that something is a volume form? Well, if you integrate it, it gives us the volume, right? So, volume form on Sn-1, right, is an n-1 form. So we can integrate it such that the integral of the volume is, okay, that's a bit of a discussion, but let's say it's the Hausdorff measure. So the integral over 1 is the same as the volume form. Volume forms are not unique, at least not in this form, right? Because you add any exact form to this, right? It integrates to 0. So volume plus some d eta is still the same as just the volume, right? So they're not unique. That's kind of a good thing. We just work with one. The one that we have over there is the popular one. That's because it's so long. -1, I -1. Then we have xi, right? This is the scalar guy. dx1 through dxi -1, dxi +1 through dxn. You see this is an n-1 form because I skipped the dxi. It's over here. And if you want to compute this or you see this, this is exactly the same if you take the pullback. So the pullback of a volume form is exactly this determinant formula that I had over there. Okay, up to the sign, which is definitely wrong. All right, now, if you write it like this, the differential is just the volume form of Rn, which is good because that's the determinant after the pullback, right? So that we will use. But now the point is, I mean, I'm not going to prove this. I'm going to hand-wavily argue why this is true, is the degree of f. All right, we defined this only for the winding number with the picture, right? This is the same as the integral over the volume form on Sn minus 1, Sn minus 1. Okay, we didn't really define the degree for higher dimensional things. There's a counting version as well. You just count the signs of the inverse of certain Jacobians. So these two notions are the same. Okay, that's really helpful. This here is great for analysis because standing on the North Pole and counting how many times the curve passes by is not very good for analysis, right? This is a beautiful formula that we can integrate by parts and everything with. But maybe that's the more intuitional formula over here, right? So how do we prove that these two things are the same? Well, one way to do it is to show this is a homotopy invariant, this is a homotopy invariant. Then we need this abstract theorem that says the degree, this one, measures the homotopy invariance, measures all the functions. So if f and g are in the same homotopy class, they get the same degree, that we know. But also, any degree is attained by exactly one homotopy class, right? It's not all mapped to one, right? It's a one-to-one relationship. That is the theorem that you have to prove. But then, what do you have to do? You just have to evaluate this for the identities, 2 times the identity, 3 times the identity, and so on, right? And then it's an explicit computation that these two things are the same. All right? But I want to, just for fun, erase this. Argue, why is this for the winding number? Because that's the only thing that we really defined. Maybe I do it here. This is the winding number, the first one. Why is this the same as, why is this formula the same as standing on the top of the North Pole and counting? Right? Again, you can abstract nonsense way, like prove it, right? But why is this the same? Where's the counting here? Well, okay. So again, this is a pullback of a volume form. Volume forms are not unique. We can always localize them, right? We can make them live only in a tiny part of the domain. So the first thing that we can say is we localize this around a point P in the target sphere, right? This is, again, this here is, I write this as the pullback of a volume form. And we can assume that the volume form lives like where we were standing around the North Pole. Okay? Again, volume forms, you can always add this closed forms. And if you, want to be everything 0 except a tiny bit, you can. So then what does this become formally? Well, this becomes, we look at all the points of f that map into this North Pole, right? Let's be generous and say we sum over them. So we sum about all the x that map into this North Pole. Let's call this n. And then we sum this guy. Okay? So this here, after this localization, more or less looks like f1 tangential derivative f2 minus f2 f1. Right? That's essentially localization. Okay, and now the observation, right, is what is this? This is a scalar product between the derivative of f, which is going around, and the curve, well, the rotated f, right? So this is f2 with a minus sign and then f1. Sorry. I write this here again. This is the sum. And then we have f minus f2, f1. Okay, and this is scalar product with the curve that's wounding around at this North Pole. Okay, x maps into n. So what is this? This here is n. Now it's not quite n. It's the negative f2 here and the f1 there. That's n perp, right? That's the rotated n. So if n is this vector, this here is that vector. Maybe in the other direction, but I don't really care. Okay, that's orthogonal to n. That's all we care about. So what is this? This is the orthogonal direction, well, picking one direction, times the derivative. So if the derivative points in that direction, and n points also in that direction, we get a plus. If the derivative points in that direction, n still points in that direction, we get a minus. There's some normalization going on that I clearly messed up, right? Or hit under the rug. But you see, this here counts the directions that we pass through this point n. Okay? And this is, at least how I like to explain myself, why, not just that, but you know, why this formula here is the same as this standing on the North Pole and watching curves pass through. Okay? And again, the actual proof goes just by homotopy theory and, you know, computing this for the identity. All right. Any questions? So that ends a bit the hand-wavy bit. So, well, now, hopefully, so we know what the volume form is, right? We don't really care for our purpose what the volume form is, we just need to know there is one. So there is something like this, and the degree is equal to that. Okay. So we have f, we know the degree is not zero. So we have the situation that we have little f such that the degree is not zero, so this guy is not zero. And we assume we have an extension capital F. Okay, and this here by Stokes' theorem is the sphere is the boundary of the ball. So this is F star pull back. This is kind of an extension, right? The volume form only needs to live on Sn minus 1, but we always think of these things extended. And there should be a D, because that's Stokes. Now, as we have discussed, F star and D, the pullback and D, they commute, right? So I can move this guy here. And now, either I remember what the formula for the volume form is, right? So for the actual volume form of the sphere, this is dx1, wedge dxn. Or I just say, I don't care, this is an n form. Any n form is a multiple of something like this, right? Either way, whichever we prefer, this here is an n form. F pullback of an n form needs to include an n-dimensional Jacobian, right? So somewhere in this thing is certainly the determinant of df. Maybe if this wasn't the precise pullback times something, right? And now the point is, this is the n cross n determinant. So this here, under the assumption that the rank is only n minus 1, is 0. Right? And so we get a contradiction that this is 0 and this is not 0, and so the identity cannot hold. All right? I would claim that even for Lipschitz maps, this is not a super obvious theorem. Right? This has nothing to do with Sobolev for now. Now, important observation, I mentioned this before, we don't care that this is the volume form. Any abstract nonsense n minus 1 form would lead to that argument. Right? All right, so we have proved this theorem. Right? And again, I'm not so sure how to prove this theorem without some explicit representation of the degree, right? So this abstract nonsense, or the, you know, the standing on the North Pole type of version of the degree is difficult to prove such a statement. All right. Now, as I said, we don't really care about that this is the volume form. And this leads kind of to curious observation. That Let's look at maps going from Sn minus 1 into some Euclidean space. And fix an omega, which is an n minus 1 form. Smooth, let it be compactly supported, doesn't really matter. All right. The observation that we could have from this is the following. This f maps into this, right? So give me an f from Sn minus 1 into Rn and compute this formula. Omega is fixed on Sn minus 1. That's a homotopy invariant in the sense that, let me call this rank homotopy invariant on W1n maps. Very long word. You can also do it for Lipschitz or C1, doesn't really matter. In what sense? So we only look at maps that have rank df less or equal than n minus 1. Okay, for f itself, this is not really that relevant because that's the maximal rank. And now we say that two maps Fg are rank homotopic. It's a word that I just make up. If the following is true, there exists a transform A going from 0, 1 cross Sn minus 1 into Rn. No manifold restriction here. H of 0 is F. H of 1 is G. And the assumption is that if we compute the derivative, the gradient of H, right, this is now on an n-dimensional domain, then the rank is less or equal than n minus 1. And this whole H is Sobolev. Okay? That's kind of a weird way of calling something homotopic, but we could. And then the statement is, then this here is homotopy invariant. Omega is fixed, we don't care what it is. Right? Omega could be 0, right? Then everything is 0. That's also homotopy invariant, trivially, right? So it doesn't say that it measures everything that can happen. It just says that if you have two functions, f and g, that are homotopic in this sense, this evaluates to the same thing. All right? Okay, and the proof is pretty much the proof that we have done. Okay. How do we prove this? Again, it's just Stokes. That's the beauty of these arguments. Just Stokes, all integration by parts. At least for the smooth case, and we will talk about the not so smooth case later. All right, so proof, like let F be homotopic to G in this sense. We want to compare F star omega minus G star omega. Okay. That's two integrals. We want them to be boundary of the homotopy. Okay, no problem, no problem. Right? Sn minus 1 and minus 1 is the boundary of this cylinder, right? So this is the cylinder without the top and the bottom, well, without this and this, right? The cylinder. And this, and with a sign, right? This, so there's a plus minus here. The yellow thing is the boundary of the white thing, right? So this integral, which looks like two integrals, is actually one integral. This is the integral boundary of 0, 1 cross Sn minus 1. H is the homotopy, right? Which at 0 is F and at 1 is G. So this is the pullback H of omega. Right? Okay, now I have one integral and I just use Stokes. All right, now Stokes, same thing, d comes here, then it goes inside. So I have h star of d omega, and I'm here on 0, 1 cross s n minus 1. Okay, good. And all I care about is this used to be an n minus 1 form. Now this guy, so this here is n minus 1. This guy is n form because there's a d on top. So this here takes into account Jacobians, determinants of gradients of h, which are, so this is determinant of submatrices of n cross n type, right? And since the rank of this guy is n minus 1, it can never be non-zero. So this is 0. Okay? Now, again, observe. I don't care what the target space is, right? You can arbitrary dimension. We don't have to embed anything, right? This always works. All right. So in this sense, I mean, not clear why we would care about it, but we have some sort of homotopy theory for maps with a defined rank. It's a bit different than what topologists would look at because you cannot define this for continuous maps, right? The rank of the derivative of continuous maps is undefined. Okay, we will have to deal with that, but okay, we can do this. Now again, why would we care? We care about this because in the Heisenberg group, this is exactly the situation you have. You look at maps into the Heisenberg group, say Lipschitz maps, and well, the Heisenberg group looks like Euclidean space, more or less, right? But one thing that you can make sure, if you Lipschitz into the Heisenberg group, the rank of your derivative will be at most, well, whatever the number of the Heisenberg group is. Hn, then it's n, right? And then you can use these theories to kind of investigate homotopy groups of the Heisenberg group, right? And that's why we cared about this. Okay, but these are just, you know, tricks. Okay. Any questions? So now we essentially have shown, right, with this whole thing, we can show, okay, if we want to consider this notion of homotopies and topology, then the n-1 homotopy group of any Rn is non-trivial because we always can embed the sphere, take a degree 1 map, right, and do this argument, and then we have a non-trivial map. It's impossible to extend. Okay, good. Now you can ask, it's very specific, right? What about any other number, right? Can you kind of combine this rank, right? This rank here was n-1, this is n-1, can we play around with this a little bit? And we can, if we understand the homotopy groups. We don't really understand the homotopy groups, so we can do it for a few examples. So this here is, think of this as S2 to S2. Right? It's a bit confusing because domain and target are the same, but okay. So now we can look at S3 to S2. Okay, and try to do the same thing. All right, so let me write down what we can do, then prove why. So the idea is now somehow to decouple this number, n-1, and the domain. Right? All right. So let me state a theorem. This is what we just had. So theorem, and this is the theorem we actually proved. Gotta find the 14 or something like this, pretty old thing. So here's the statement. For any, okay, n larger or equal to 2, you will see the numerology and you will know what it is. There exists a smooth map, C infinity from S, and now the numerology is terrible. For n minus 1, I will simplify it in a second. Into, okay, this doesn't really matter, R2n plus 1, such that there exists no map F in W1 for n minus 1, so it will be 4n of the 4n ball into R2n plus 1, such that F on the boundary for n minus 1 equals little f, and the rank of df is less or equal to 2n. All right, let's go through this again. So for any n larger than 2, that's a typo. I already multiplied everything with 2. Yeah, so that should be a typo. That should be n larger than 1 because I suggest to look at n equals 1. I think then this becomes clearer. So if we look at n equal to 1 or larger or equal to 1, there exists a map from n equals 1, this is S3, into, okay, R3, fine. R3 is relevant because S2 is a subset of R3, such that we don't find any extension into W14, B4, whatever that number is, this can also be larger, which extends the original F without increasing the rank above 2. Not above 3 or 4 or something like this, above 2. Okay? All right. And again, I said that this here is relevant because the S2 is in here. And so what are we using? We're using the Hopf invariant, right? And Hopf maps. Okay? All right. So, how do we prove such a statement? Well, the whole point of everything else here is that all we can do is really integration by parts, our main technology. So what needs to be given to us is a formula of this type. Right? And now we know from S3 to S2, the homotopy groups are rational, so they are Z, and there's a nice formula for that. Right? So that the homotopy groups are non-trivial is due to Hopf, hence the Hopf map. And the Hopf invariant is also due to Hopf, that's how we proved it. But then there's a very beautiful formula. Again, there's like a formula via linking numbers. So the Hopf invariant, go from S3 to S2. Look at the map. So the usual definition that we learned is, okay, take a point here, look at the inverses. If this is the right point, like if this is a regular point, then the inverses from S3 to S2 should be one-dimensional circles. Right? We have a three-dimensional thing mapping into S2, so somehow circles have to be mapped to a point. And so we take the inverse of this point. So that's the inverse. That gets mapped to this. And we take another point, take that inverse. And the joke is we look if they are linked or not. Right? We compute the linking number between those. So red circle inverse, orange circle, this is the inverse. If they're linked, or we count the linking number between the two, how many times they're linked. If it's 0 times, the Hopf invariant is 0. If it's 5, then it's 5. And again, you see this is kind of a very nice, intuitive, maybe way to think about the Hopf invariant, and then you have the Hopf map and you can compute this, but it's not so useful for our purposes to compute stuff like this. But, lucky for us, there is the Whitehead formula. Which goes like this. It looks crazy, but it works. Well, I don't really understand topology, so for me this looks crazy. All right, here's the formula. You take, I go from S3 to S2, this works for everything, right? So you look at the map from S3 to S2. You take the volume form, which is a 2 form, right, of the S2. All right, what do we know? Well, if we look at F of omega, okay, that's F star of omega, right? The pullback of this volume form, I call this omega, so I have to write less. This is a closed form, right? If I compute D of this guy, then the D commutes. And now F is, well, maps into S2, and we can argue, okay, we say this is the rank, right? The rank can be at most 2. This is now a 3 form, right? So this must be 0. And you see, all we need for this is the rank. We don't care really that this maps into the sphere, but okay. Right, so this is a 3 form, so this is 0. Okay? So we have a 2 form on here, which is closed. Now, this is the S3. This is R3 up to the North Pole. This is pretty nice with respect to 2 forms. In particular, any closed form is exact. Right? This is because this is high dimension, this is S3. So this is closed. So it's exact. Because we live on S3, this is wrong on S2, right? And so what do we get? We get that F star of omega is d eta. Now, I don't want to write this. So the eta is very non-unique, right? There's a lot of choices here. Doesn't matter. I will pretend it's not and just call this d inverse of F star of omega. That's a very nice notational choice. Okay? All right, we can define this. And now, well, there is some way of thinking of this as linking, but I don't really understand it. We compute this integral. F star of omega, it's a 2 form. D inverse, that's a 1 form. 2 form, 3 form. And that numerology works for all of these things as well. And this is S2n minus, so this is S3. So that's a 3 form on a 3 manifold, so this makes sense. And the theorem, I assume by Whitehead, that's why it's called, is that this is the Hopf degree of F, or the Hopf invariant. Okay? Now, I didn't define the, well, I drew a picture for the Hopf invariant. We don't really care about the Hopf invariant per se. We just care about the result by Hopf from the 30s, which says there is a map that this is non-zero. Right? That's the Hopf map from S3 to S2, and then he proved it for any of these 2n minus 1 to Sn in the even case. Right? So that's why we have the numerology. So the statement is the existent F from S3 to S2, it's super smooth. It's, in this case, really this Hopf map, that this is not 0. Okay? Good. So this is the thing that we have, right? Or that we kind of discovered in the topology literature. And we wanted to prove this, again, for the reasons of the Heisenberg group. Okay? So, now how do we prove this theorem? Exactly the same way as before, it just gets a bit longer. So, we have this formula This is an F from S3 into S2. So that's a subset of R3. So we have a map into R3. It has this structure. And this formula is non-zero. Okay, so we have 0 is not this integral on S3 or whatever numerology you want. What do we do? Stokes, right? F inverse, sorry, this is not F inverse, this is F star. F, little f is the same as capital F. Now here, this is a bit of cheating, right? So somehow behind this, one has to prove that it doesn't matter what D inverse we choose. Right? Remember, D inverse of this, or what we said is it's the map that comes out of the Ram cohomology, right? Which is very not unique, right? The D inverse is this eta. We can change this eta. So we have to show that the change of eta doesn't change the formula, which is essentially the same. It's Stokes theorem. Okay? Anyways, so 0 is not this. Now we use Stokes. So Stokes, okay, we have two terms. We go to B4. We have D F star omega, wedge D inverse F star omega, plus, so the D hits this, and then there's plus or minus, I never know, doesn't really matter. And then we have D F star omega, wedge D inverse F star omega. Okay? Okay, that's Stokes. And now we see, okay, what do we have here? Here we have, this is F star of D omega, wedge something. This is now, this was a 2 form, this is a 3 form. We assumed the rank is 2, right? So this here is 0. Here, we don't have this. We have F star omega wedge F star omega. Now you could get excited and say, hey, maybe that's 0 because it's something against itself, but it's not, right? We're exactly in the dimensions where this is not 0 necessarily. However, the pullback of omega wedge, the pullback of omega is the pullback of the wedges. So this here is actually the pullback of omega wedge omega, which is a 4 form. It's even bigger. So this is still 0. So this whole thing is 0. Right? And this proves, as long as the rank is at most 2, this F must, this formula must integrate to 0. So it means that we cannot embed the Hopf map into our setting, which we can, and so contradiction. Okay? So that proves this sort of theorem. And again, if you think about the Heisenberg group, if you know the Heisenberg group, right, this here, I wrote this because this is Hn. Yeah, right? And you see that this essentially implies, if you now do the technicalities, that the 4n-1 Lipschitz homotopy group of the Heisenberg group, that they are maps that you cannot contract, however you want to call this. Okay? Okay. So we can do this, and then we thought, okay, so what does this tell us? It tells us somehow we can do these sort of arguments whenever we have, or we have a chance at doing these arguments, when we have such a formula. Right? If we have a nice integral formula of our homotopy groups, maybe we can do something. If we have no such formula, we have nothing. Right? So the big question is, when do we have such formulas? Yeah.
Take any complex boundary, put a topology like non-genius, take its boundary, replaces them by the boundary. Will this still hold?
Yes. This doesn't use anything about the precise Sn-1. Right? I mean, I use the Sn-1 because then we have homotopy groups, right? We like to think, or I like to think of them as sphere maps from the sphere, but this is not used, no. right? This can be pushed in a lot of directions. In particular, we did this for the Heisenberg group, but I didn't want to introduce the Heisenberg group, so we just do it in Euclidean, right? But there is this question, for what sort of homotopy groups? Okay, first, there are two questions here. The first question is, we have now like different examples of rank, domain dimension, and target, and we get non-trivial maps of some sort, right? The question is for what numbers can we plug in here, here, and there so that this works? I have no example where it doesn't work, right? But we have a few examples of combinations of those where it does work. And where does it work? Where we find a homotopy group that we can write in such a form. Okay? Now, the good news is somehow they are classified, which is crazy, but this is Sullivan and Novikov. There is this notion of rational homotopy group, which I like to say is simply if the homotopy groups is Z, right? It's not Z2 or something, it's Z, then such a formula exists. And this is due to Sullivan and Novikov, and I cannot read either of those papers, right? They're far away from my capabilities. But even better, Hart and Riviere computed this. So they kind of gave like an analytical description of this argument that says whenever you have an homotopy group, so you can just look it up on the databases that we have, you have a non-trivial homotopy group, some form of this integral version, this D inverses notation by Hart Riviere, exists, and then you can start thinking about whether such an argument works. Okay? And what we are doing now is, so you do this, and then you start with, so what homotopy groups of spheres are have no torsion? And essentially we covered them, right? There's not much more left. So you say, okay, we're done, right? The sphere is the nicest object, but we don't really find many more formulas of this type. That's it, right? That's the end of it. But who said that we have to work with spheres? So maybe you look into SON, but then you get scared of SON, and but maybe we just leave the setting of manifolds. And so what we are currently writing down, we'll see when this is done, is we take, 2 is enough, but we couldn't figure it out for 2, so we just took more. We take wedges of spheres. Okay, so this is Sn. One point is joined, and we take Sn and Sn, and we do a certain amount of copies. Then, and I think this is Whitney, I don't know, there's a theorem that these, essentially we have a numerology for which of those are rational homotopy groups. And so let me write a theorem with some random numerology, which again doesn't cover everything, but it covers something. So n larger or equal to 2, that was wrong before, so let's see. L is larger than 0, k equals n plus L n minus 1. Then we take these, the volume forms of each of these guys. Okay, so this maybe is omega 1, this is omega 2, omega 3. We choose the ones that are disjoint. Okay, so they exist n minus 1 forms. These are these omega i's, and a map which is smooth from Sk into, and we go into Rn plus 1, okay, because these are Sn. Okay, I went here to Sn spheres, all right, such that the following formula is non-zero. No, this is, maybe let me put this. Okay, this theorem is known. There's nothing, I mean, you ask any algebraic topologist that is somewhere close, they know this theorem. This is not the point of the theorem is that we can use this. So I still will shamelessly write our names here. Ison, student, Hiwash, Park was my postdoc, myself. No idea when this will be done, but it's essentially done. So we find a non-trivial map for this form, right? Again, that's not a new theorem at all, right? It's the formulation and the conclusion that there exists no extension F in W 1K plus 1 on the K plus 1 ball into Rn plus 1 such that the rank of df is at most, and we have n forms, so it's n, n. So we get this sort of result. You can see some of them overlap with the hop and some others don't, right? So we kind of see more. We cover more numbers of combinations of this dimension, and non-trivial maps. And the proof, once we have this map, that this behaves is exactly the same, right? This is the Stokes theorem. No change. Yeah. So now for the next thing I wanted to talk, yeah, maybe I just mentioned it briefly. Any questions about this? Yeah? No. No. Abelianity, I don't care. I don't know. I don't think that, I mean, abelianity means if you concatenate two, right? That is not the same as concatenate them the other way around. I don't think this plays a role in this formula. But somehow, whenever you expect such a formula, you do expect that the homotopy groups are really, you can get any number n. You can compose F with F with F, or do it twice, 3 times, and then you get 3 times the original ones. So any such formula somehow rules out that you measure something like Z2, right? So you cannot measure torsion elements with this sort of thing. So that creates an issue, right? So pi 4 of S2 or something we have no formula for, so we don't know what to do. All right. Any other question? So in the last minute, let me show you what how we extended this. Which is related to like a very fancy conjecture. We didn't really get anything new. By Gromov of embeddings into the Heisenberg group. So if you know the Heisenberg group, some weird space, which goes like R2n plus 1, but it has this weird metric structure, right? And you can ask yourself, okay, can I embed a k-dimensional set? Like called the ball BK, can I embed it into the Heisenberg group? What you relatively easily can show that if k is less or equal than this n, no problem. And if you're Lipschitz, it's not so difficult to show, no way, once you're above n plus 1. So in that sense, the Heisenberg group is like n-dimensional, right? You cannot fit anything n plus 1 dimensional. But this changes if you look at Hölder maps. So this is for Lipschitz. This is relatively easy. For Helder maps, the question is if you can embed anything n plus 1 dimensional into the n-dimensional Hausenberg group, which is Helder. And there we know this is doable. If alpha is less than 1/2, then we don't measure anything. And it's not doable if alpha is maybe m plus 2 over m plus 3 or something like this. So if alpha is large enough, this is not doable. And in between, we don't know. All right. And so we have like a proof of this sort of statement, like revisiting this statement, which is relatively easy. And I will briefly mention this the next time and discuss kind of that this is essentially this stuff. Okay, that will be the main gist of the how to prove this statement. We hope that we can get lower, but for now we cannot. All right, but we do this tomorrow. Thank you. Oh, sorry, yeah. Yes. All I can do. Now, W1P for P less than the dimension, you would say. The issue is these things won't be integrable anymore. I will talk about this, but the point is essentially we do this for smooth maps and everything works by approximation. But if P is less than the dimension, so this here is not integrable, then you don't have convergence of the approximation. So this is where it fails. And this is also the problem for Helder maps, right? Then something fails and some things work. Yeah, so Stokes' theorem holds, the way I like to think of this is Stokes' theorem holds when everything is smooth, right? Omega is d omega. This holds when everything is smooth. Now approximate. Right? Now you can, if this is an L1 and this is an L1, you can approximate just by modification and things work. If these things are not in L1, Stokes' theorem should be taken very carefully, right? Or not at all. So my recommendation for Stokes' theorem is always do it for smooth maps and work with approximation. Then you're on the safe side, right? So in particular, if this is a pullback of a, if this is an n-1 form and this was the pullback of d of the n-1 form, right? Then this is an n form. So this is somehow something of phi, whatever this omega is, and then it's the determinant of d phi. This here goes like d phi to the n. Right? And that's why we need Ln. There's a little bit of these compensations that one can try to play with. I will talk about this, but that's kind of, yeah. All right, any other questions? All right.
Any question from online participants? Yes, thanks, the speaker again.